Yes, thank you, Professor Yaşar. Professor Rahrovi, you are welcome to present your study,
these programs. Title: Hybrid CAS and block pulse functions for numerical solutions, fractional population growth model. Contents: abstract introduction, fractional integral, CAS wavelets, block pulse functions, implementation of the method, error estimation, conclusion. Abstract: in the present paper, a computational technique is proposed to solve the fractional population growth model. For this purpose, the operational matrix of fractional integral was used for cosine and sine wavelets. The error estimation is provided. Finally, numerical solutions of presented model and comparisons with two other methods are presented to show the validity and efficiency of the technique. Introduction. For a long time, fractional calculations have improved their positions and efficiency in various fields of science, such as mathematics, engineering and technology, biology, social science, and etc. For example, applications such as modeling of nonlinear earthquake oscillations, color vibrations, fluid dynamics, dynamic economics, signal processing, and so on can be mentioned. References 2 to 4.
Professor Rahrovi, can you hear me? I think he's having internet problem. We will wait a couple of minutes. Professor Rahrovi, can you hear me? Professor Rahrovi, please open your microphone. Professor Rahrovi, please open your microphone.
Okay.
Yes, we can hear you. Please share your screen. Professor Rahrovi, can you hear me?
Yes, yes.
Yes.
Screen share.
Please
problems.
click on green. Please click on green button in Zoom screen.
Okay.
We cannot hear you. Please share your screen by using green button or screen share. in the zoom button, zoom screen.
Okay.
Yes, we can see. Also, please make it full screen by using F5. Thank you.
Therefore, with the increase of the domain of applications of fractional calculations, many techniques are presented for solving fractional differential equations, such as Adomian homotopy perturbation method and the Bloch-Pass functions methods, Haar and Lejeune wavelets. A combination of orthogonal functions such as legend, Chebyshev CAS wavelets, and others with Bloch-Pass functions is a useful technique for generating efficient approximation of function on L power 2 R. The main and useful advantage of using orthogonal bases is to turn the main problem into a system of algebraic equations. Therefore, it can be concluded that the method will simple has a high speed of calculation during executions. This can be done by limiting the extension of series in orthogonal base functions to obtain unknown solutions of the method under consideration by using operational matrix. Fractional integral, the Riemann-Liouville fractional integral I alpha of the order alpha greater than 0 on L1 several intervals 0b is defined the form below. Some of the most important properties of I alpha are as follows. I power 0 above x equal fx و CAS wavelets. In this section, we bring some of the required definitions of CAS wavelets. Then we obtain the function approximation using CAS wavelets and Bloch-Pass functions. CAS wavelets are defined as follows, where CAS index M is equal cosine 2mpt plus sine 2mpt. And in 0, 1, the compact support of CAS wavelets is as follows. Support sign index in MAT. Here we present the usable symbol and notation related to CAS wavelets as follows. Bloch-Pass functions. An M set of Bloch-Pass functions on interval 0, 1 is given by where important properties of Bloch-Pass functions include disjointness, orthogonality, and completeness. Function approximation by Bloch-Pass functions. Any function F elements of L2 interval 0, 1 is represented using the Bloch-Pass functions and above relation as follows. About T semi-equal summation Fi bit is equal transpose F b out T or equal transpose B out F, where Fi is statement. Function approximation by CAS wavelets. The set of CAS wavelets forms an orthonormal basis for F blank L2 interval 0, 1. From the recent phrase, it can be concluded that its function fx determined on interval 0, 1 is extended by about semi-equal summation this statement. Also C and psi are two power k 2m plus 1 time 1 column vectors as follows. Operational mathematical integral CAS wavelets can be extended with M' term of black-box functions where this statement equal is established. Therefore, psi index M' of t is equal phi M' time M' P' of t, where phi index M' time M' is equal diagonal phi and is 0, phi and is index 1, and phi n for n, this statement where lambda is in point-wise product. Implementation of the method. Now we use CAS wavelets to solve the following fractional population growth model. Kappa E alpha U of t minus U of t plus U power 2 of t plus ut integrals 0 t u of t u of tau d tau is equal 0. U and this u self is equal u index 0. Alpha greater 0 smaller than 1, where the expression ut is the scale population of identical individuals at time t, and the coefficient kappa is equal C of AB, is a non-dimensional parameters. Let d alpha ut semi-equal transpose u psi t, where u is the unknown coefficient vector using the initial condition and above relation we achieve. Then u and u of t is equal semi-equal transpose a b index m prime tau. The rest of the expressions are obtained in the same way. Finally, we obtain a system of algebraic equations as follows, which is a non-linear system of equations. By solving this system, the unknown vector u and then a are specified. The approximate solution to the desert problem is obtained in the form as u of t semi equal transpose a b index m prime of t. Error estimation. We can check the accuracy of the approximate solution u of t semi-equal transpose a b m prime t of t. Error is equal absolute statement. Numerical illustrative examples of the population growth model have been solved in several articles 9 to 30. In this section, we use the CAS wavelets method to solve fractional population growth model. Case A. Firstly, we set u index 0 is equal 0.1. Alpha is equal 1, and solve the classical population growth model for different values of kappa, which is plotted in figure H. It is shown in figure 1 that for small values of kappa, the solution grows very fast. To this figure, alpha is equal 0.1, 0.2, alpha 0. Figure 8, the graph of numerical solution of the classical PGM with alpha is equal 1 for different value of kappa for case A. Case B, for the next attempt, we take U index 0 is equal 0.1, alpha is equal 1, 2, and solve the problem with different value of kappa. Figure 2 shows the graph of numerical solutions for this case. The graphs show that the population rate grows faster for small values of kappa. As kappa increases, the population growth rate decreases. Case C. In this case, we set U and this 0, index 0 is equal 0.1, kappa is equal 0.2, and change alpha. The result is plotted in figure 3, which show that the solution increases faster as kappa decreases. Figure 1, figure 2, the graph of numerical solution of FPGM with alpha is equal 1 or 2 for different value of kappa for case B. Kappa alpha is constant 0.5, but with different value of kappa 0.1, 2, 3, 4, 5. Figure 3, the graph of numerical solution of FPGM with kappa is equal 0.2 for different values of alpha for case C. Conclusion. In the present article, we solved the FPGM by using CAS wavelets and Laplace function with collocations technique. Analysis of the solution behavior shows that it increased with considerable speed along the logistic curve and starts to decrease exponentially again after reaching the maximum point. When the order alpha reduces, then the critical time and domain of the solution reduces, whereas the exponential decay increases. For small values of kappa, the solution grows very fast, so the accuracy of the solutions in the first of the interval is not very good. Then, for a high accuracy, we need to increase M', but it is not suitable. To demonstrate this problem, we can implement method again nearby 0. References. Thank you for your attention, and